Hey math fans, Alex here, and in the previous video we introduced systems of linear equations, and we essentially started off with a very basic example of a 2x2 system, and we discussed the various cases in which that could happen geometrically. Then we moved on to a couple of examples of 3x3 equations, and we said that although 3x3 equations can look entirely different and geometrically can be very complicated and different, if the solution set is the same, which it very well could be, we call the systems equivalent. And we said that we were going to consider the case of n by n systems in the rest of this section and ask ourselves the question, can we reduce this system, which could be very long, because n could be like 100 or 1,000, can we reduce that into one that's easier, albeit possible, to solve? The answer is, yeah, probably. So here's my claim, and you can take this as a theorem. We are going to kind of prove part of it. And I believe that proofs in math are useful if you learn something from doing the proof. Other times they're just necessary, especially if you're studying pure mathematics. But I digress. Here's my claim. If you have a system, that's going to have a solution set. I can do three things to that system and keep the exact same solution set. I can do three things that are going to try to make it simpler to solve, and the solution set will be the same. Here are the three things. I'm going to try to motivate each one. So the first thing you can do is you can take two equations and you can just flip-flop them. Okay, so if you have equation 1, equation 2, you can just interchange them. That's really, hopefully you believe this, right? Because each equation gives a little bit different information, and information is commutative in a sense. If I tell someone fact A and fact B, and I also tell them fact B and fact A, I'm giving them the same information. Okay, so you should buy that it's going to have the same solution set. The second one, multiply an equation by a non-zero scalar. Okay, so if I have an equation, like, I don't know, this one, for instance, and maybe this entire solution set is, x1 is a value, x2 is a value, xn, so you have an n tuple as a solution set, and I decide that I want to multiply this equation all the way through by, I don't know, 5. I take this times 5, that times 5, all the way up to this times 5, and this times 5. If I do that, I will not change the solution set. Again, hopefully this makes sense, because if I want to revert to the original equation, I can very easily just divide everything by 5. Okay, so that's not really going to change anything. But it is still something worth talking about. And the last one's probably the most complicated one. You can take an equation and replace it by adding that equation to a scalar multiple of another. So I should probably tell you what a scalar is. A scalar is just a real number. Okay, so it's in the real number set. And in this case, we prefer it to be a non-zero scalar. Okay, clearly it's true if that scalar multiple is 0. Okay, but let me just kind of show you an example of when we did that. So in order to solve this system, I want to go back to what we did. Okay, what I did was I essentially replaced equation 2. I replaced it with equation 2 plus 1 times equation 1. So I added this entire equation to a scalar multiple, 1 times this equation. Okay. Another thing that I did is you can think of me replacing equation 1 perhaps. I replaced equation 1 with equation 1 added to a scalar multiple, -1 times equation 3. So I can multiply any of these equations by whatever scalar I want and add that to this equation and then replace that with the result. Okay, so in other words, if I wanted to replace, say, equation 3, if I wanted that to be replaced with, say, equation 3 plus, I don't know, 10 times equation 2, I can do that. And after I do that, the solution set will remain unchanged. Okay, so you've seen that done. Maybe it didn't make complete sense why you could do that. Okay, but I'm here to kind of try to motivate the example. So before I go into like the theoretical proof, let me just show you a more basic example. So let's say that, going back to this instance, if I have like equation 1, equation 2, equation 3, that's going to have a solution set that's going to be some ordered triple, x1, x2, x3. Now, if I replace equation 3 with something like, I don't know, let's say equation 3 is really equal to equation 3 plus 5 times equation 2. I should be more specific. This is 5 times equation 2. I'm really replacing equation 3 with that. My new equation is going to be equation 1, equation 2, and maybe we'll call this equation 3 prime. Okay, but it's really just this. Okay, well, first of all, the equation remains unchanged if I multiply equation 2 by a scalar. Okay, so really that's not the confusing part. So this 5 isn't what's making this confusing. Because if I buy this, then I should buy the fact that I can multiply equation 2 by any scalar and it's still true. So the tricky part is, why can I replace an equation by adding it to another equation? And that's where you learn these terms like solving by elimination, and you maybe didn't understand why you're able to do elimination. But again, let me try to motivate the example for you. Let's say that I have a scale, okay, and on that scale I have equation 1. Okay, so equation 1 is going to say, I don't know, I'll just use a simple example, a1 x1 plus a2 x2, and that is going to equal some b1. That's what an equation is. You're saying the left-hand side equals the right-hand side and the scale's balanced. This is equation 1. If I take equation 2, I can add that to the scale and it should still be balanced, because I should have specified this, shouldn't I? So a11 and then a12. Okay, because if I have a21 x1 plus a22 x2 equals b2, this is equation 2, and I add that to both sides, then this plus this keep my scale balanced. So that's why you can take one equation and replace it by adding another equation to it. And you're going to end up with the same solution set because everything maintains that balance. Okay, so you should kind of have all of that in your mind as we're kind of proving this. Okay, so how on earth are we going to prove this? Well, I'm not going to prove 1 and 2. 1's obvious, and 2 you should do as an exercise. So really the only thing we're going to focus on is 3. So how are we going to see that 3 is true? Well, first things first, we have to consider the following equations. We're trying to show that the solution set remains unchanged if I replace one equation with a scalar multiple of another. Okay, so I just have to pick 2 equations out of the n. N could be like 100. I don't care about the 100, but I have to pick 2 arbitrary equations and go from there. Okay, so I'm going to index them as follows. So I'm going to index the first equation with an I, and I could be anywhere. I'm letting it roam essentially. Okay, so I have a I1, x1 plus a I2 x2 plus yada 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 plus a in xn equals bi. That's equation I, in a sense. And the second equation that I have, we'll do j. So this is a j1x1 plus a j2x2 plus yada 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 plus a jn xn equals bj. Notice same unknowns, same unknowns, same unknowns. Okay, the only thing that's different is that the coefficients are different, because this is equation I and this is equation j. And I should, again, probably specify a couple of things. Okay, first of all, I probably shouldn't allow it to be j, because then they're just the same equation. Okay, and both I and j are either 1, 2, all the way up to n, where n could be as big as you want. Okay, so this is our original system. It's part of our original system. There's really n equations. I didn't write all of them. I just picked 2 of them. The other ones are going to remain irrelevant to this discussion. So I'm going to call this system that includes 1 and 2, I'm going to call that star. And star, along with the rest of the equations, is going to have a solution set. Okay? So we're going to go ahead and say that the system, including the 2 equations that I've denoted star, we'll say that has solution set x1, x2, all the way up to xn. Those are the unknowns, and of course they're going to be replaced with something, but those are the unknowns that solve both of those equations. Okay? What we have to do now is we want to show what? Well, we want to show that for some scalar we'll call c, which is just a real number, for some non-zero scalar, we want to show that replacing, we'll say, equation 2 with c times equation 1 plus equation 2. Okay, and this thing I'm going to go ahead and call, I'm going to call this 2 prime. Okay. That is not going to change the solution set. Does not change the solution set. In other words, it's going to have the same solution set. It's going to have the n tuple right here is the solution set. So again, I'm going to try to formulate it. So I'm going to keep these same 2 equations. In fact, I might as well just copy them, because what I'm going to do is going to be so similar. Okay. So we're going to take this, and it's going to be so close to that. Couple of differences. Equation 1 is going to remain unaffected. Equation 2 is what I'm going to change. So instead of 2, it's going to be 2 prime. And to get 2 prime, we're going to take equation 2 and we are going to add a multiple of equation 1. Okay? So what is that going to look like? Okay, well, we might as well do a little bit of work to figure out what that is. So if 2 prime is the same thing as c times equation 1 plus 2, let's do this term by term. So the first term, I'll do the first term. So I'm taking c times that term plus the original from equation 2. Okay, so I'm taking c times ai1 x1, and I am adding the original from equation 2, which remember was aj1 x1. Okay, so then the first term, I can factor the x1 out, and I get that this is equal to c ai1 plus aj1 times x1. Okay, so this first term is going to be, I'll put it in parentheses, of course, c ai1 plus aj1 x1. So that is what I get in general when I replace equation 2, which remember was this, when I replace this with a scalar multiple of equation 1 added to equation 2. This is the so-called elimination method. Okay, and you can imagine that all the terms are really going to look just like that. So what is the second term going to look like? It's going to be, say it in words, a scalar multiple of equation 1 added to equation 2 plus yada, 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 plus, running out of room here, but c, since I'm running out of room, I might just do this, plus c ain plus ajn xn, and that will equal not bi, but that should equal c times bi added to bj. So this is clearly an entirely different system because equation 2 looks very weird. We're going to call this double star. What we have to show is that star and double star have the same solution set. If they do, then this is an allowable operation that we can do on the equations that won't change the solution set. All right? Okay, so basically the problem that we're trying to solve is we have to prove that the n-tuple x1, x2, all the way up to xn, we have to prove that that solves star if and only if it solves double star. Okay, so let me just explain what this is because occasionally I use it in proofs. Again, I'm trying to not make this as proof-oriented as possible. However, some things just need to be shown, and I think this is one of them. Because this is something that you were taught in grade school and maybe didn't understand exactly where it comes from, but there's actually a theoretic underpinning here. Okay, so what does this if and only if mean? So I'm just going to kind of go off on a tangent. So if and only if, so if I have a statement P, and I say P if and only if Q, what I have to show is if I have P, start with P and then show I have Q, and I have to prove if I have Q, then I have P. I have to prove two things with the if and only if. So I have to show that if the n-tuple solves star, then it has to solve double star, and I have to show that if the n-tuple solves double star, then it has to solve star. okay? So I'm actually going to show kind of the reverse, and then I think the original direction is easier. Okay, so I'm going to show, so we'll say, you know, part 1, if the n-tuple x1 through xn solves, we'll say double star, then it solves star. Okay? Okay, so how are we going to do that? Well, as in most proofs, if you're doing it directly, I will write proof because we're actually going to start the proof now. We're going to assume the n-tuple solves double star. And then we're going to somehow show that it solves star. What does it mean that the n-tuple solves double star? Well, let's look back at what double star was. And I'm not writing that again, so we're just going to copy that. Okay, so these can be taken as facts now. We know that x1 through xn is going to solve these two equations, and thus it's going to solve the rest of the n equations. Okay. So how are we going to show that it solves the much simpler equation 2? So why does x1 through xn solve the original equation 2, which remember was just aj1 x1 plus aj2 x2 plus yada 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 plus ajn xn equals bj. Because clearly equation 1 in both star and double star were the same. So the only thing I have to worry about is why, if it solves 2 prime, why does it solve 2? Okay. And the answer to that is the fact that I can write 2 prime. Okay, so note that I can write equation 2 prime in kind of a special way. I can rewrite it as follows. Okay, so if we look at equation 2 prime, I'm going to kind of break that up as follows. So I'm going to distribute the x1, the x2, and the xn. And what I'm going to have is equation 2 prime can be written as CAI1 x1 plus CAI2 x2 plus yada 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 plus CAIN xn. That's what I get when I distribute the x1 to each of these first terms. Just the first terms, that's what I get. I'm going to get n terms overall. Then I'm going to add in the second ones. Okay, so I might as well do that here. So plus aj1 x1 plus aj2 x2 plus dot 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 plus ajn xn. So just pause the video, verify that what I have written down here on the left-hand side of this and this are the exact same. I'm just rewriting 2 prime in this way. And that is going to equal CBI plus BJ. Okay? So we know that x1 through xn has to solve 2 prime, so then why does it solve 2? Well, the very simple reason is if I look at 2 prime more carefully, I might notice that all of these terms have a c in them. So since c is a non-zero scalar, I'm allowed to divide both sides by c. And after I cancel the c's out, I notice that this part right here, which I'm going to go ahead and highlight, this part is equation 1. Right? This is equation 1. And we know that equation 1 is true, meaning that ai1x1 plus ai2x2 plus yada 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 plus ainxn, that indeed does equal bi. So since they're the same, we can just cancel them out. Right? If you have 2 things that are the same on both sides of an equation, yeah, you can subtract and cancel them out. So this completely goes away. Not that completely, but. And now what we have is we have this quantity, but that's just equation 2. So we get that x1 through xn plugged into equation 2 has to satisfy that. Okay, so just to summarize here, so what we get is that after we plug in for 2 prime, after rewriting it, we can cancel out the part that looks like equation 1, and then we get that x1 through xn has to solve 2 prime, which is actually aj1x1 plus yada 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 plus ajnxn equals bj, which is equation 2. So we showed that if this solves 2 prime, which is a part of the double star system of equations, then it has to also solve 2, which is a part of star system of equations. So thus, we've shown that if x1 through xn solves double star, then it solves star. Okay. So then part 2 of this proof would be to show that if the n-tuple x1 through xn solves the original system star, then it solves double star. And the proof is going to be an exercise, both to save time and to give you a valuable puzzle or exercise to do on your own, which should be actually a lot more straightforward than going the reverse direction if you follow this kind of procedure. So write it down, verbalize what you're doing, and of course, ask me if you have questions. But this kind of motivates the idea behind the 3 operations. And going back up, the main point is that we now have 3 operations that we can do to a system of n equations and n unknowns, and we can always do these 3 operations. We have 3 tools in our arsenal now to simplify an n by n system into something easier to solve. Okay, so what I'll say to end off this video is with these 3 operations, and you're going to want to remember them. with those three operations, we can essentially transform an n by n system into something that we're going to call a triangular form. A triangular form. And that triangular form can easily be solved using a method called back substitution. Both of which are new terms and both of which will be discussed in the next part of this video. Hope to see you there. Have a great rest of your day.